So welcome everybody to the second day of this series of workshops on the improvement of the performance of canals with geosynthetics. So we had an excellent series of presentations yesterday and that were covering the different options, applications of geosynthetics in canals. Today we are going to be focusing mostly on seepage control, so geomembrane liner and similar products. I would like to remind you to use the question and answer option, which is in the bottom of the screen. In the center of the screen, you have a Q&A with two bubbles on top of it. Please click on this button when needed and enter a question. So we have a time dedicated at the end of the workshop to address these questions and answers. So from there, we will start immediately with our first speaker, who is Hervé Plusquelec. Hervé has now over a total of 55 years of experience between an irrigation agency in Morocco, an Italian consulting firm, and a donor agency, the World Bank, followed by 25 years as an independent consultant. I don't want to calculate the total number here. He started experimenting with geomembranes in 1965, known as thin plastic films at that time. Later, he has been involved in the preparation and implementation of all the irrigation projects financed by the World Bank, where geomembranes have been used. He has published a number of articles and documents advocating adoption of advanced technologies in irrigation, of irrigation engineering, mainly canal control and canal lining, including an ICID publication on the use of geosynthetics in canal lining. He is the second author of the book under preparation in collaboration with J.P. Giroux, which will be published in 2022. So from this, please, Hervé, the floor is yours.
Yeah. Let me... Then I have to sorry. That's it? Is it works now? You can hear me?
Yes.
Okay. Thank you, Eric, for these presentations. Indeed, I experiment with a short section of a canal with plastic film, it was called at that times. Unfortunately, it didn't last very long because the local farmer found another use for the plastic film, and that was the end of it. But anyway, it was a good experience to know that vandalism or stealing is part of the problems. I have divided my presentation in 4 sections. The first one is the use of geosynthetic in irrigation sector is lagging behind other engineering applications, with one exception I will discuss later, the case of Egypt. The second part will be about the benefits of canal lining and the famous debate about to-line or not to-line irrigation canals. The third one will be the preference for concrete lining by irrigation agency and by their consultant, a subject which has been already touched by Jean-Pierre Giroux yesterday, and I will complete my presentation with the World Bank experience and other lining of canal with geosynthetics. All types of geosynthetics have been used in all civil engineering applications, either to improve the watertightness of hydraulic structure, to reinforce the foundations generally in transportations, and to meet the requirement for the environmental protections of the groundwater. Also mining. This is a few examples in the dam engineering, and Mr. Squero will revise the figure maybe later. About 280 dams so far has been waterproof with geomembrane, with some of them are up to 200-meter height. So that shows the confidence of the civil engineer in the geomembrane, which has been used for such a structure which the total safety is a major concern. It has also been used to reinforce the soil, generally for roads, which is the case here, especially on weak soil, like a pit. It's also used in transportation, so navigation canals, and also for the treatment of solid waste by the creations of waste storage landfill. It's also used for the waterproofing of reservoir. This case is in Kazakhstan, but this reservoir can be used for water supply or for irrigation purpose. But in terms of canal lining, the irrigations is the only sector where the use of geomembrane is not widely used or widely considered at the time of the detailed design. One exception, one country is a really a remarkable exception. It is the case of Egypt. In Egypt, about 80% of the 3.5 million hectares are irrigated using surface water from the Nile. And the total length of a canal, which is controlled by the government, for the main canal is 13,000 kilometers, the secondary canal, which are the branch, 32,000. And in addition of that, you have the farmer control canals, what is called the Mesca, and below the Marwa, which is about 80,000 kilometers. The Egypt starts to some interest in using a geomembrane through a USAID funded research, which is called Egypt Water Utilization Project, EWUP, in 1984. Under this project, a few applications, a pilot application were done, some of the Nasser canals, but there was some failure of concrete line, the side slope, and they also experiment with short sections of canal using LDPE. This is a failure of this subsection of the Nasser canals. And the recommendation of that report, which were valid 10 years before, where the geomembrane, the thick geomembrane were not yet developed, were to line the small canal with 10 mils of PVC protected with soil cement, and for the largest canal to use 10 or 20 mils, which, if you are not familiar with this terminology, 0.2, 0.5, that means still very thin geomembrane protected with concrete. This was in line with the use of geomembrane in the US and the former Soviet Union before the 1980, using not geomembrane, plastic film, which were 0.2 millimeter. You can see on the left in what was part of the Soviet Union in Kazakhstan, and on the right with LDPE, which are the two different materials used by these two countries in the US. But in late 1990, Egypt initiated the Toshka canals to irrigate the new Nile river valley, taking water from Aswad Dam. And this is still probably the largest applications of geosynthetics for canals with 20 million square meters. And now Egypt has embarked on an even more pharaonic projects, which is the Egypt Canal Rehabilitation Projects, with the first phase include 9,000 kilometers, and the minister yesterday told us that the total phasing of this project will cover about 20,000 kilometers. The technology which is used is about 1 foot of rocks covered with a thin concrete layer. I move to the second part of my presentations now, which is the benefit of canal lining and the debate about lining or not lining canals. There are about 325 million hectares which are irrigated in the world, of which 125 with groundwater. That remains 200 million hectares are irrigated with surface water and supplied through networks of canals. If we exclude the traditional irrigation systems, there are at least 120, 130 million hectares which are irrigated by canals, which represent probably 1 million kilometers of canal and a few billion of square meters. That gives you an order of magnitude of the potential market for application of geomembrane in canal lining. The benefit from canal lining on this slide, the most important one is reducing the seepage losses, and that is a benefit which is generally used for the justification of canal lining at feasibility level. It also improves the canal hydraulics, reduce the waterlogging salinizations, and reduce the maintenance cost. We can say that the daily seepage losses per square meter for inland canal range from a few liters per day for clay soil to 500 or even more for sandy soil. The typical losses which is adopted in the feasibility study in the Indo-Gangetic plain is about 25 centimeters, 250 liters per square meter per day. Roughly speaking, we can say that about 1/3 of the total water which is diverted at the headworks of an irrigation system, 1/3 is lost in the field channel, another third is lost in the canal system, which leave about 30–40% of the diverted water available to meet the crop requirement. That means, in other terms, an overall efficiency of 35% for irrigation system, which is the value which is obtained when you make a diagnostic or a performance of an irrigation system. In some countries, the performance is for canals could go up to 40–45%, but could be also as low as 25%. The variable which influence the seepage losses, there are three important ones: the characteristic of the soil, of course, the permeability of the soil, the geometry of the canal, and the depth of groundwater, and the positions of the water table. There are other factors. This is at the project level for a new canals. For all canals, the quality of construction, the aging of the existing canal are also important factors. And minor one is the chemistry and the temperature of water, which has a minor effect, but when you are trying to determine the seepage losses by different methods, that was the case in Pakistan a few years ago, and Chris Davy will maybe talk about it. It was very difficult to determine why we have a difference between the two methods. The maintenance cost, reduction of maintenance cost, both the experts from the Soviet Union in the past and from the USA conclude that the maintenance cost has reduced by about 2/3 after lining of the canals. The capacity of the canal by lining is double because the roughness coefficient is also reduced by about half. So, but if you line the canal several years after initial construction, which is sometimes the approach which is adopted in some country, it's a costly decision because the wetted perimeter has nearly, and the freeboard has nearly doubled. This is to show the impact of water logging and the impact of the seepage losses from canals on the water logging and salinization of the adjacent soils. Worldwide, there are about 10% of irrigated land which suffer from water logging and 70 million hectares which are salt affected. Now I move to conclude this section with a debate about water resource and irrigation canal manager. The water, some of the water resource experts mentioned that the water which is seeping from a canal is not lost. The water has not disappeared. The water can be captured again by pumping in the groundwater, or can be used further downstream until it reaches the sea, of course. However, the advocate of canal lining will argue that the cost of pumping and the impact of energy demand for pumping the groundwater has enormous impact on the energy sector. For example, in India, 245 billion cubic meters are pumped every year for irrigations. And this is equivalent to about 1.5 times the volume which is stored in the Aswan Dam and 6 times the volume which is stored in the Three Gorge storage dams in China. When the canal are online, you have a deterioration of water quality and the impact on health by pumping groundwater. And these are also a water logging and salinization of adjacent soils. I will stop with this debate, which is at no end, and I will conclude this part of my presentation by saying, if the decision is taken to line a canal systems, the manager of the irrigation agency should adopt a durable design options, given that lining increase the construction cost by at least 40%. And if the efficiency of the lining is only a few years ago, you lost a lot of money. The third part of my presentation is the preference by concrete lining by irrigation agency and their consultants. There are 2 methods for lining the canal with concrete, which is the alternate panel and the canal lining machinery moving longitudinally along the canals. And with the rigid canal lining, there are also the brick lining, which is essentially used in South Asia. It is estimated that the seepage losses from a canal which has been recently lined with concrete is about 7 to 10% of the losses before lining. But this percentage could increase after a few years of operations enormously, and to the point there is a very severe deterioration that there is no difference between before lining and after lining after a few years. Why the rigid concrete lining deteriorate over time? This subject has been already addressed by Jean-Pierre Giroux yesterday, but I will summarize it here. It could be because of the climatic conditions, the freezing and thawing, which affect a number of countries with or area which is above the 40-degree latitude north or south, northern China, Central Asia, the Caucasus, Canada. The second one is the soil conditions, which is gypsum, which is the most important one, which affect part of Spain, most of all the Middle East countries, Iran, Iraq, Syria, the sinkhole in the karstic area, swelling clay, and these affect a large part of the Deccan Plateau in India. And finally, the loess soil, which are found locally in China, and residual soil, which could be found in Brazil. But on top of this, the poor quality of construction and the non-compliance with the technical specification at constructions also participate or contribute to the deterioration of rigid canal lining. For example, compaction of embankment and poor placement of concrete. I have seen some irrigation project, will not mention in which country, where the layer of compaction was about 70 centimeters between layers. These two photos, show a functional failure, at least on the left side. The cracks, the longitudinal cracks, is enough to make to increase the seepage in these canals about the same that without lining, and the same on the right side, which is a canal in Kosovo, Iber canals, Iber Leping canals, where the panels have just settled because of the settlement of the foundations, probably when the canal was put into operation for the first time. This is not only functional, but it's a structural failure. And in this case, there is no way to rehabilitate by putting some geomembrane on top of it. It has to be removed and rebuilt. Another example, this is the Yambash Canal in Uzbekistan. These precast panels were laid over a very thin plastic film, as it was done in the Soviet Union 20, 30 years ago. It took 15 years for this canal to deteriorate before the water and the sand percolates. This plastic film has no welding, and therefore it takes time for the sand to pass through the overlap and then through the joints, and until the point that the whole structure just collapses. However, concrete lining canals is not, a failure of concrete lining canal is not ineluctable. This is one example of a canals in Morocco, the Doukkala main canals, built more than 50 years ago, which is still in excellent shape. I visited this canal 2-3 years ago. I could not find any cracks. The reason for that are 3 reasons for that. The first one, the thickness of the concrete is 15 centimeters, which is 50% more than the design standard used for most of the country, for which the main thickness of lining is 4-inch, 10 centimeters. So the second point, this slope, the size slope is 1-to-1, or not 1.5-to-1. So the granulometry and the composition of the concrete was experimentally tested before placing the concrete. And the last point was the excellent quality of supervision. And now I address the last part of my presentations, which is the World Bank experience with canal lining, with geomembrane. Over a period of 60 years, there are only 5, 6, 7 projects which has been financed by the World Bank using geomembrane instead of concrete lining. 5 are already completed, and there are 2 ongoing projects in Central Asia, Uzbekistan, and Kazakhstan. So roughly 1 per decade is not really a great performance. The first one was a project in China, Xinjiang province, the extreme west of China, where 5 million square meters of geomembrane were installed about 700 kilometers of canal. The Chinese did not import the geomembrane. They import a factory from Italy, and they manufacture the geomembrane, but again, they use a very unique combination for the material itself. It's a mix of HDPE, LDPE, and LLDPE. I don't know if they were expecting to get the benefits of these composite mix, but the geomembrane passed all the tests with the exception of the hydrostatic test over a cone. The thickness of the geomembrane was 0.5 millimeter, which is still too thin to get the excellent welding, where you need at least 0.7 or 1 millimeter. The precast, the protection of the geomembrane, the Chinese use different methods. On the slide is a precast panel. They also use a local stone, where it's close to a torrent from the mountains. They use also clay. And for welding the geomembrane into, which is produced in a 4 or 5 or maximum 6 meter wide, they prefabricated panels in factory conditions. And you can see that they are using the most advanced, or at that time, that was already 15, 20 years ago, welding machine. You can see on the left of the machine that there is some undulations which show that the welding was not perfect. But anyway, it was for them an increase from 0.2 to 0.5, 2.5 more. It was already the most I could obtain from the Chinese to increase the thickness. And they did that after a visit of the, oh, sorry, I will come back. The geomembrane is at another example, this time in Vietnam, of a geomembrane which is protected by precast panels. Another example, which is one of the 2 ongoing projects, which is aligning with the bituminous geomembrane in Kazakhstan. There is a large choice of geosynthetic and also a different options for the application technique. The geomembrane is a summary of what has been said yesterday, and which will be developed later by the following speaker. There's a polymeric, PVC, HDPE, a different polyethylene, polypropylene, hypalon, EPDM. They can be smooth or they can be structured to increase the frictions. The thickness is variable from a 1 to 2.5 millimeter. There is also the bituminous geomembrane, the GCL, geosynthetic clay liner, the composite geosynthetics, and other. The installations, they can be exposed, they can be protected, they can be placed in dry conditions or in some, the most sophisticated one, under water. These are an example of a project in India, the Pench Canal in Madhya Pradesh province. On the right, you can see the conditions of the lining, concrete lining, which is really in peace. There is no other way to describe it, probably because of the swelling clay, and it had been removed and replaced by a bituminous geomembrane. There are other options, which are the geocell. We don't know exactly if there's a geocell here filled with concrete. It's below, it's just a geotextile, or if there was also a geomembrane. There is a geomadress. I have seen 2 examples, one in Indonesia and one in Iran, myself. And the bituminous geomembrane can be installed directly on the subgrade, or like here on the right side, it is the canal, the Société Canal de Provence, to repair a canals, which is still in good condition, but probably some cracks, which was installed 50 years ago. About the normal life of a canal. There's another example that we'll have a presentation later, which is about the geosynthetic cementitious concrete mat, an example in Chile, the Bellavista canals. Some of you who are not too familiar with the geomembrane may have some difficulty, say, how to select, get the criteria to select the geomembrane. There are so many different shapes, different forms, different ways to install them. So the first consideration is the operating life. It is clear that the criteria for waterproofing high dams, a roller compacted concrete dams, vertical, is not the same that for lining a tertiary canals. So the level of control of the seepage losses varied depending on the scope of the works. The site conditions also, Jean-Pierre Giroux yesterday mentioned the temperature and the problem of considerations for seaming and the problem of wrinkle because of the expansion of the geomembrane with high temperature. The wind is also an important factor at the time of installations. And to come back to my short experimentation in Morocco 60 years ago, the risk of by animals, vandalism, and stealing, whether it's considered as vandalism or not. The interest in geosynthetic is growing, as a conclusion, because an increasing competition for water and also the disillusionment with a concrete rigid lining. Just a word of publicity for the book that is under preparation by Jean-Pierre Giroux and myself, which will be available next year, published next year. And to conclude, a photo showing the dream of an irrigation system manager, where there are no operational losses and no seepage losses because of the geomembrane and because of the automation of canal control. There are a number of irrigation systems in Australia now, which are probably the dream of many of the participants to this seminar. Thank you so much. Thank you for your attention.
Thank you, Hervé, for the very interesting presentation where you really set the performance requirements for the canal lining. Much more than focusing on the material, it's really about why we line and what we need to achieve by lining. That's, I think, the core of the question is addressed in your presentation. So for question for Hervé, please use the Q&A button. There was already a couple questions posted. Please post more as you feel is necessary. At the end, we will address all these questions. So our next presentation is going to be from Chris Davey. So Chris is an independent consulting engineer with 50 years of experience, and he specializes in irrigation and drainage. He has worked on the major irrigation and drainage projects in Pakistan and India, and has worked in many other countries, including Cambodia, Ethiopia, Mali, and elsewhere in Africa. His experience in geomembrane canal lining started in 1998 on the 160 kilometers of canal lining on the Fordwa Eastern Sadijia project in Pakistan. He has been a member of World Bank and AFD supervision missions to Egypt from 2012 to 2018 on the Integrated Irrigation Improvement and Management Project, the National Drainage Program, and the Farm Level Irrigation Modernization Project. So Chris, please, it's your turn.
Hello, can you hear me? Can you hear me?
Yes.
Yes.
Thank you very much, for your introduction. Good afternoon, everybody. Yesterday, we heard a very good and detailed explanation by Gerard on the need to line canals, and I strongly agree with his recommendations. And today, Hervé has also stressed the need for lining canals, and you can see the damage that has happened on canals which are not been lined. My talk today is looking at the practical problems of retrofitting canals in canal systems. I can't cover everything that needs to be covered in this short presentation, but I hope that everybody will get a hint of the problems that are there. Why do we talk about retrofitting canals? Well, basically because if we need to look at why do we need to retrofit canals? We also need to consider the effects of retrofitting canals on a system. So we need to look at conveyance efficiencies and water savings. And we also need to look at the practical issues that occur when you talk about retrofitting canals. We also look at the social issues and the technical issues. I think yesterday we had the minister mentioning that they had to deal with social issues and the farmers in trying to deal with when you start doing the works that they are doing on lining the canals within Egypt. So why are we retrofitting canals? Why do we need to do lining? Everybody's mentioned the need that there's a shortage of water coming up. There's a problem of climate change. Ideally, you would like to line canals from the start, in other words, new canal systems. But most of the major canal systems have already been constructed. We look at the works in the Nile Delta, we look at the works in the Indus canals. So it's a much more complex issue that you need to deal with, because the work is not just the physical work of choosing a canal to be lined, but we also need to see the effects of retrofitting canals to the population who are already in the area. So which canals should we choose to retrofit? In Egypt, the minister has shown that the works are now ongoing on lining the works for the main canals and in the distribution canals. But we also need to look at the water losses which happen on the rest of the system. I think we've just seen from Hervé a discussion also on the amount of water which is lost in the smaller canals. Egypt depends very much on the water from the Nile for its irrigation. In fact, all the water that they have really comes from the Nile. And if we look at the savings, if you talk about improving the efficiencies in the whole canal system from a saving of, say, 10%, we can be saving something like 5 billion cubic meters of water per annum. This is probably more than the water which is used in industry and for drinking purposes in Egypt. So it's a major effect that we had by looking at the amount of water which can be saved. So where can the saving be made? The works which are ongoing are looking at lining the distribution canals. These are the large canals in Egypt, and you look at the efficiencies from the first figures we had, that's something like, say, 20% of the water which is lost in the supply from the Aswan Dam through the whole system, something like 20% is lost in the distribution of that water in the main distribution canals, in the main canals. But we should also look at the losses in the smaller parts of the system. And the figures which were given by Hervé and also by others is that something like 40% of the water is actually lost in the meskas and marwas. In other words, at the lower part of the system, you can be losing up to 40% of the water. So the improvements that you can make at that level would have a significant effect on the overall water savings in the system. So what does the unlined canals or the marwas in Egypt, are fairly simple canals. They have small canals, but there are huge numbers of them. The Marwas are similar, that they are small canals, and the savings that you can make are immense. Some of the works which are going at the moment are looking at brickline canals. Now, we've looked at the works that have been done by others, that bricklining has a very significant effect in its early years, that you can have the savings of up to 20–30% of the losses. So you could improve the efficiencies from the say 40% loss, you can reduce that to maybe a 20%, maybe a 10% loss. But over a period of time, these also break down, and the problems are there unless you can put in a lining, which then means that the brick is there only to protect the lining work. In Egypt, they have actually gone down to putting in buried marwas in a small area, something in the order of, I think, about 200,000, about 100,000 hectares, or 200,000 fedans have got these new buried marwas. The efficiencies of the marwas, of course, are very high, that the water losses between the pump station and the farmer are only possibly 2%. But these are very expensive. But the costs can be met by the farmers themselves. So looking at the status of irrigation in Egypt, which has just been covered by it, you can see that the overall irrigation efficiency in Egypt is very low, something like 40 to 60%, due to the evaporation, seepage, and deep percolation. We can look at the improving the seepage and deep percolation losses by lining. And the water savings that can be made in the lower end of the system could ensure that the present irrigated area in Egypt can be maintained, and that the water requirements can be satisfied even with possible reductions of water availability from the Nile. Now, I'm looking at retrofitting canals, and what are the problems that which you are going to face when you start retrofitting canals? You have to remember that the areas that you're dealing with are heavily habitated. There are people in those areas. There are people who are depending on those areas. So the problems that we have can be divided into social issues, technical issues, and then the financial issues. I mentioned the financial issues. In these marwas that the department had been putting in, the costs of these are being borne by the farmers. The costs are calculated for both for the pump station and the marwas. The farmers form a water user association. The costs are calculated, and then each farmer is expected to pay his percentage of the costs of putting the system in. But the other social issues that you need to deal with also deal with issues such as land tenure, the traffic movement during construction, oil spillage, hygiene, protection of children. All of these are there because this is an existing area. It's an area which is under cultivation. It's an area which has people moving within it who have got a lifestyle, etc., which is dependent on the canal being operated and working continuously. Land tenure is a particularly sensitive issue in Egypt. Many of the farmers have land holdings of less than 0.25 of a hectare, or half a fadan. And the farmers depend on the crops for their livelihoods to feed themselves and their family. So even small deductions in the land are critical, and water supplies are critical. The farmers have a fixed rotation, and their yield and their crop holdings and their livelihood depend on them getting this water. So when we look at retrofitting a canal, or retrofitting, which means rehabilitation of the system, in effect, it means there are going to be interruptions, which means that you need to deal with the social issues and the people who are there. Of course, retrofitting the canal, you've got all the benefits. There's no doubt that the farmers are going to appreciate that if you improve the canal system, if you improve the way in which the water can be supplied, you improve the banks, that hopefully that the quality of the water will improve. And certainly the tail end of the systems, with the efficiencies improving, the tail end of the systems will get better quality water. And the water quality for agriculture, with improved efficiency, more of the area will be irrigated with the good quality water. in Egypt, there's a tendency at the tail of the system that they use the drainage water. The water which is discharged in the drains from upstream areas is then repumped and used in agriculture. So improving the system by putting in a geomembrane to stop the losses will mean that more farmers can benefit from the better water supplies. But the technical aspects of retrofitting canals, if you have an existing canal which is lined, well, you get all the benefits, reducing seepage losses, eliminating waterlogging, etc. But there'll still be the problems during the construction phase of the farmers being disrupted, the water supplies possibly being disrupted. But if the existing canal is not lined, then retrofitting the canal would have a significant effect on the operation of the system. So we need to look at the design aspects. And in looking at the design aspects, we need to go back to the farmer. We need to look again at the awareness of the farmers that the whole system is going to be changed. We need to look at the way in which the farmers and the stakeholders can be involved in the whole process of redesigning the canal system, of retrofitting the canals with geomembrane. So I don't apologize for always going back to saying that there's the technical aspect, but there's very much also the farmer, the participation, the stakeholder aspects, that these need to be integrated if you want the system to actually work. The unlined canal system in Egypt and elsewhere in the world, the small canals in Pakistan and India where I've worked, they tend to be very rough. The maintenance program means that the slopes have actually degenerated, so you end up with steep side slopes. You end up with a canal which is following just a natural flow path, and so the overall design needs to look at a complete change in the design section. Now that sounds simple, but when you're dealing with people who are very concerned with the space that the canal takes up, and if you look at the initial photograph I showed for the marwas, you can see that if you consider changing the section, you're going to be taking land away from the farmers on either side. And so there needs to be a way of looking at how to maintain that section, keeping the same profile for the canal through the farms. Now, the change in canal profile is not necessarily a problem in Egypt in the larger canals, because Egypt is slightly unusual in that the whole system is based on the premise that the farmers will actually be pumping from the main canals and the distributor canals. And so the problems in the design, the change in the canal profile, the problems there are going to occur on the Mescas and the Marwas, where you're looking at gradients, where your Manning's factor may change from, say, 0.25 to 0.2, and that's going to affect the velocities and flow depths. And that changes the water levels through the system. So if you have outlets, etc., which depend on a definite water level, then changing the type of canal from being an unlined to a lined canal may mean that you need to change how the outlets operate. If they're open flumes or pipe outlets, then these need to change. Part of the design is also a matter of looking at the social facilities which are provided, because when you're redesigning the canal, then there's going to be a need to look at how farmers get access to a canal. They're changing it from a simple slope made of soil where people can walk, where animals can walk. If you change that to being a canal side slope, a concrete slope, then access is not so easy. And so that needs to be considered during the design of it. Now, part of the work is, once you start looking at the retrofitting of canals, you need to involve everybody right from the start on the contractual aspects. What is the stakeholder going to participate? How is he going to be working with the various people involved at the construction phase? There needs to be clarity in the responsibilities and the interaction between all the people who are involved at the construction phase. The construction activities will certainly disturb the farming activities. This might mean that the contract needs to include some way of paying compensation. It'll mean needing to organize formal meetings with the farmers so they're aware of the works which are going on. It'll need a way of solving disputes. And then during the construction, there needs to be a way of maintaining the critical water supplies. These farmers cannot afford the idea of having no water, so the work needs to be carried out possibly during the closing periods. Each of these major canals have closure periods either once a year for an extended period of up to 3 or 4 weeks, or they may have closure periods when they have a rotational system. So farmers may get water, say, once every 7 days, in which case there may be 6 days where work can be carried out. The alternative, which has been carried out, is looking at diversion. So the canal is diverted into a temporary location while the construction work is ongoing, and then the canal is put back into its original alignment. And we need to keep the original alignment because farmers, as I say, they keep their own land holdings. They don't like to consider, they generally will not consider taking a movement of the canal and losing part of their land. But diversions are very costly. The decision on whether to divert or not may depend on the type of concrete that you're going to be using. If the contract allows the contractor to have cast in situ or to use precast units, then this will affect how the work is actually constructed and will affect, you know, how much time he needs in order to do the lining works. For the large canals, there may be some rights of way and there may be some access. And so the distance between major structures will mean that they can use larger equipment. But if you're looking at the smaller canals, such as the Maras and Mescas, there's probably, as you saw in the first photograph, there's no right of way besides these canals. The farmers cultivate right to the edge of the canals. There's probably not even a walkway on many of these canals. So the contractor in those locations may need to consider using precast panels or other forms of lining in order to upgrade the system. Again, the stakeholders will need to be aware of what's going on. The scheduling that is being carried out will need to be in discussion with the farmers so that they know exactly what's happening. On the project we were involved with and which Hervé was also aware of, is the one in Pakistan where we did diversion works. So you can see this small scenario, the first one showing the canal is diverted first onto the right-hand side. The works are carried out with the diversion canal operating, which maintains the water at the same level. And then the diversion works are removed and the canal is returned to its original shape, original alignment. Some of the diversion works are being carried out even in Egypt. This is the IIIMP project where the canal needs to flow during the low season. So they had pipes to divert the flow while construction work was in progress. On the right-hand side, you can see they've actually put a diversion adjacent to the canal. So again, it allows the construction to continue and the flow will then be diverted back into the main canal when the work is done. In Pakistan, the work was done using precast slabs. And these slabs you can see for the smaller canals are slabs which can be handled by individuals. And then the side panels are placed on a compacted soil, and then the joints between them can be concreted into place. Using the local labor as a way of improving the benefits of the project. And on the left, you can see that the hand dressing and preparation of the canal was all done by hand dressing. And then the material is placed with the assistance of all the local laborers. Placing concrete in situ, again, done on the small scale with local people all participating in the lining works. And these works, you can see, these are photographs taken after 15 years. I haven't got any of the more recent. The project was completed in 2000, so possibly somebody going there can see if the works are still looking in the same condition. But you can see that these canals lined on the left-hand side with precast with cost in situ. On the right-hand side, they can see the small-scale canal with concrete panels. And here again, the base was placed with cost in situ concrete in the bed. And on the sides, you can see there were thin concrete panels. Again, they've been operating for about 15 years. Some of the options that are used there, we're looking at precast vertical units. And these were, again, the canal is in relatively good condition after 15 years. Maintenance of canals, of course, is a problem. Canals often get treated with disrespect, with rubbish thrown into them. So, but the concrete side, you can see, is looking in good condition. I talk about having to discuss with the farmer the need for access to canals. In this particular area, the canal has been broken purposefully by a farmer who needed to have access for canals. So you can see concrete is in very good condition, but the one slab was removed and the soil is then put in when the canal starts flowing in order to maintain the canal, but the farmer needed access for animals. And on the right-hand side, you can see this was broken into by locals for access as well. So finally, if we look at the conclusion we can come to, is that global warming and climate change will reduce the water available for irrigation, which means that we need to look very seriously at how to save the water which is presently used in canals. So retrofitting the existing irrigation canal systems with geomembranes will reduce water losses and could result in significant water savings and would reduce waterlogging and salinity. Those are the two items which are stressed in any of the discussions you have in places like Pakistan. The process of retrofitting canals with geomembranes will have a significant effect on all stakeholders who must be consulted at each stage if you want the project to be a success. The technical impacts of remodeling canals for geomembranes will change the whole operating system regime. And that means that you need to look at the design from the top to the tail to ensure that at the end of the retrofitting, the end of the remodeling, that all the farmers are still supplied with the water that they were expecting to. And the successful implementation of retrofitting a geomembrane canal lining will depend on the interaction and support of all stakeholders at all stages. Thank you very much.
Thank you, Chris, for this very interesting, holistic approach to the canal lining, to the irrigation sectors. So now we will move on with the presentation by Bertrand Breul. So in his capacity as a global technical director for Axter Coletange Inc., Bertrand brings 20 years of engineering experience with over 13 years in the geosynthetic industry. Instrumental in the development of standards and certifications for coletange worldwide. Overseeing training, research and development and quality control has given Bertrand a unique perspective on how the market perceives and reacts to coletange, not only in North America, but within all regions where Axter conducts business. Bertrand was a managing director for Canada based in Montreal, QC for over a decade. In this role, he was responsible for all technical and sales marketing functions for Axter Coletange Inc. This experience affords clients in North America a broad range of industry and market-related expertise. So Bertrand, please.
Thank you for this introduction, Eric. I'm going to share my screen now. So I think it's functional now. So I'm going to present you the use of bituminous geomembrane for waterproofing large canals. Firstly, I'm going to remind you the BGM structure, a typical structure, and then the advantages of BGM geomembranes for waterproofing canals. And then I'm going to share with you some references and examples. So firstly, the BGM structure. There are two types of products. The first one is a double reinforcement BGM. It's the let's say, historical product, and it has been manufactured since the early 80s. It's composed with the first reinforcement is a glass fleece. It's used for dimensional stability purpose. And the second reinforcement is a non-woven geotextile, which gives the mechanical properties of the geomembrane. And both reinforcements are impregnated with the SBS modified bitumen, which give the waterproofing properties and also the edging resistance of the geomembrane. Since 2020 and 19 also, there's no more blown bitumen used to impregnate the geotextiles. The underside is a terrain film, and the upper side is a standard just for finishing purpose. The second range of products is a single reinforcement product. It's a most recent technology, and the two previous reinforcements are replaced by a single one, which is a polyester glass composite reinforcement. The rest of the product is the same. It's a thinner product, but with similar performances. And it's most flexible in terms of width of the product. So usually BGMs are 4 or 5 meter wide. With the single reinforcement, we can easily do different width from 1 to 5 meter. So it's quite interesting to line smaller canals. So you can decide the width you need and just install it lengthwise. So it's faster and also limit the amount of seams. The key advantages of bituminous geomembrane. The first one is a very low manning coefficient. It's 0.012. It's the same as, let's say, newly concrete lined canals. But as you know, concrete solutions tend to crack in time because of changes of temperature and also because of their low tensile strength. It's very sensitive to the quality of the support. So when you have swelling clays, for example, whereas BGM is thermically stable and is not affected by changes of the temperature. And also it has a good flexibility, around 60% of elongation, which allow to adapt to let's say, different settlements. So the second advantage is an excellent puncture resistance. So behind that, there's two things. The first one is what you can see on the top left corner. The liner, during the installation, when you have place constraint, you can drive with small machineries directly on the liner just to help during the installation. And the second point is that with this high puncture resistance, you can install the liner on earthen canals, compacted, and cover it with different type of material. It can go up to riprap, as you can see on the bottom right corner, but most usually it's gravel. The next advantages is the ability to remain exposed. So in some areas of the world, it's a very interesting option. Bituminous geomembranes have an excellent durability on exposed condition and high UV and weather resistance. the following advantage is an easy installation. Installation is quite easy in a wide range of weather, thanks to the low thermal expansion coefficient. So if you have either high temperature or high variation of temperature, there won't be any wrinkle on the liner. So you can install it along the day without problems or difficulties. And also because of its high surface mass and good flexibility, it provides a good permanent contact with the soil here under the liner. So, and also if you may expect high wind, the weight of the liner is a good advantage. Still in terms of installation, you can weld it to a wide range of materials like concrete, so concrete pipes, but also any kind of concrete structure, to steel pipes, and in some very special cases, you can weld it to rock. And it's mechanically fastened. And then in terms of maintenance, it's quite straightforward. When you have repairs to do, it's just welding a patch on top of the existing liner if there is a defect. And if it's small repairs, you can do it with the, let's say, local crew, which could be maintenance crew or local farmers. And you can also do underwater repairs due to the density of bituminous liner that are more than one, so more than the water. So if there is small repair, you can do it without emptying the canal. And the last but not least, in terms of safety, it has safer non-slip surfaces. So people and animals could walk on the BGM surface without slipping. So, for example, on the left, they needed to fence the area because of dangerous slippage in the canal, whereas, as you can see on the right, this small video, even if it's wet, some dogs can walk on the steep slope of the canal. So now I'm going to present some of our references. The first one is the rehabilitation of Canal de Provence in France. So Canal de Provence is a concrete canal, and it has been built in the 60s. Sorry, it feeds around more than 100 cities with over 3 million inhabitants, and also it feeds 80,000 hectares of agricultural land. So most of the cross section we have for this canal is the side slope are 1 vertical to 1.5 or 2 horizontal. On one side of the canal there is compacted fill. In some places they have swelling clay, and as a result, some of the concrete slab have cracks, as you can see on the photos, and some old expansion joints that are open. So they wanted to secure the water supply and mainly secure their structure. So they wanted to improve the water tightness of their canals. That's why they choose a BGM. So they firstly build cofferdams on 200-meter sections, and then they install a bypass just to maintain the flow of the water for their clients. So they dry this section and they use 4.8 millimeter thick geomembrane, bituminous geomembrane. On each panel, three portions of the panel were welded to the concrete, so 2 on the side and 1 transversally. And it was mechanically fastened on each side on the top. So there was no anchor trench. And to finish, to do the finishing, they had a concrete slab at the bottom and also concrete curbs on each side to avoid vehicles or try to avoid vehicles driving into the canal. So on purpose or not. Since 2016, 3 kilometers of canal were rehabilitated. Next example is the Nagpur Canal in India. So here you have a typical cross section. The design discharge was 90 cubic meter per second with an speed of water of 2 meters per second. The liner was installed in 2019, so it faced 3 monsoons, which is an important event in India. So you see the state of the concrete parts. It's totally destroyed, let's say. And they cover it with a new bituminous geomembrane. One of their main reasons to choose this liner was the NSF certification. So it's NSF 61 certification that allows the use of this membrane with potable water. So here you can see they removed most of the concrete parts, but they kept the one which was in good state. Otherwise, they redo the cross section of the canal and compacted it. Here you can see different structures, so connection around pillars and also gates and concrete structure. This is another example. It's the Natchezela Irrigation District in USA. They reline, let's say yearly, around 4,000 square meters of geomembrane. And the particularity here is that the maintenance crew was trained by the manufacturer, and so that when they do not have any maintenance to do, they are able to reline the canal by themselves. So just renting an excavator, and then they install the liner by themselves and weld it also. We are going now through some shipping canals for the British waterways. Here you can see the liner is connected on vertical concrete structures, and also covered with quite rough gravel. It's another shipping canal in France. Part of it is installed at the bottom of a concrete structure just to improve the water tightness, and rest of it is installed on compacted earth, and covered then with geotextile and gravel. So this is other type of project. I don't want to take too much time. this is a canal in Austria, and so you can see there is a small berm on the top of the slopes just to allow to install riprap. So, and you can see the flexibility of the liner that is highlighted here. And then this project in Chile, it's a hydroelectric power plant located in the Maule region of Chile. It's a 5-kilometer long canal with a maximum flow of 7 cubic meters per second. The initial design was with shotcrete, and at the end they choose a bituminous geomembrane of 3.5 millimeter thick, and it gave them a 30% saving compared to the initial design. So to conclude, BGM has been used as a lining system for canals since now 35 years, and it has been used for a wide range of application, and it has also been deployed on top of either compacted natural soil or on top of existing concrete. The manning coefficient is for sure better than excavated earth, and also, let's say, the same as new concrete line canal, but in the long term, it will be better than concrete lining canals, and it's also time and cost effective versus concrete lining canals. Thank you.
Thank you, Bertrand. A very, very interesting presentation. I see that we have more and more questions and answers to address at the end of the workshop, so that's very good. Thank you. So the next presentation will be from Alberto Squero. Alberto was awarded a degree in hydraulic civil engineering and his professional engineering license at the Turin Polytechnic in Italy. After 17 years working in Italy and Africa to build roads and bridges, to rehabilitate hydraulic structure, he joined Carpi, an Italian-Swiss group offering design-build solutions for the waterproofing of hydraulic structures such as dams, canals, tunnels, shafts, and reservoirs. Alberto has been responsible for the design, supply, and construction of waterproofing systems on more than 170 dams, 40 canals, 15 hydraulic tunnels, and 50 very large reservoirs and pumped storage scheme. He has been involved in several researches on material properties and manufacturing of geosynthetics. He is the author of several patents on installation of geomembranes, including underwater. He is the inventor of several patent rights regarding installation of geomembranes in the dry and underwater. Since 1995, he is also the CEO of the Carpi Tech Group. He has coordinated the ICODE European Working Group on Geomembranes and Geosynthetics as facing materials on dams, who prepared the new ICODE Bulletin number 135 on this topic. He has received several awards, including the IGS Award in 2000 and the Geosynthetics GSI Award of Excellence in 2006. So GSI is a Geosynthetic Institute. He was named ICODE Honorary Member in 2020. He is the author or co-author of more than 200 papers relevant to use of geomembranes, mainly in hydraulic structures. So, Alberto?
Okay. So I start my presentation. Okay. The main benefits of the PVC geocomposite system in canals are, can you hear me now? Yes. They water tightened and the entire surface, including the joints. They withstand action of UV, ice, debris. They withstand differential settlements. Because of their smoothness, they allow increase in the water flow and they allow monitoring of the performance. This is shows how the exposed geomembrane can increase the water flows because of the smoothness. And can resist a very high velocity. And in this picture, we can see how beneficial is the installation of the geomembrane by reducing the head. We have the top line where the water was before the placement of the geomembrane and where it is now. They resist turbulence. They resist placement of massive stones, which are not puncturing the geomembrane. Here is the application in a hydraulic tunnel where there were cracks in the existing liner, and the geomembrane was able to fix the cracks, to cover the cracks, and the mountain stopped to slide down. So it was for safety reasons. I cannot see part of my screen. Okay. Main criteria for designing a PVC geocomposite waterproofing system are: for covered geomembranes, there shall be sufficient sufficient weight of ballast and puncture resistance to create the ballast. For exposed geomembranes, they shall be strongly anchored to the subgrade to cope with water velocity. They shall be UV resistant. They shall have a drainage system. In this sketch, you see some example of how the geomembrane can be installed in canals, covered or totally exposed. For geomembranes totally covered, the geomembrane is placed over the deteriorated subgrade and covered by reinforced concrete or shotcrete. Here we have a picture taken in 1973 of Ala Bussolengo Canal in Italy, where the geomembrane was covered by shotcrete in the bottom and on the slope. This was a pioneer project when there was less confidence in the performance of exposed geomembranes. Then there is the option of the geocomposite covered only on the invert, and this applies to canals with heavy traffic for cleaning operation or invert. This is a canal in France in 1989, or in Switzerland, made in 1993. Then there is the other option of the geocomposite fully exposed. Then the geocomposite is anchored with lines of stainless steel profiles. Number, type, shape of profiles depend on the water velocity, cross-section, and strength of subgrade. This is a very good picture taken at Poschiavino Canal line in 1979. After more than 40 years in operation, no maintenance was required. This is the installation of an exposed geomembrane in a large canal in Germany, made in the year 2000. Or this exposed PVC geocomposite installed in a canal in India since 2008. We have the possibility to increase the water flow in a canal by placing an exposed geocomposite. This was the case of Senhora do Porto Canal in Portugal. The objective of the scope of the works was to create the waterproofing and increase the water flow. This was obtained by heightening the walls of 10%, placing the geomembrane very tight on the surface against the wall and the bottom. And the result was that because of the membrane stopped the leakage with a very good smoothness and the heightening of the walls, it was obtained 90% increase in water flow, 90%. Another application is the application of geocomposite partially exposed in earthen canal. And depending on the type of subgrade, several options are available. For the ballast in berm, the geomembrane is obtained by creating a berm in the upper part of the slope. Here we can see a canal in Austria, where the berm was created. The geomembrane was placed and covered by stones. The other option is to create the ballasting of the geomembrane by adding soil in the upper part of the slope, which is supported by a beam which is anchored to the slope. Again, this is another part of the same canal in Austria. And we have exposed geomembrane and covered geomembrane. The beauty of the system is that the installation of the PVC geocomposite has no adverse aesthetical environmental impact. We have another case of which was mentioned by Giroux yesterday, the take-up for canal remediation in New Zealand, where the geomembrane was installed in this canal, which is 26 kilometers long, and the geomembrane was installed in 7.5 kilometers stretches, 3 stretches, which were more affected by the leakage. So these are the 3 sections covered by the geomembrane. 2 cofferdams were built in each section. The canal was dewatered by pumping and fish transfer. The canal was reprofiled, and the installation of the geocomposites started in the canal. All welding were done by automatic welding machine, and the strict quality control was applied to all operations inside the canal. So the geocomposite is exposed except on the top part of the slope and in the bottom. The entire installation was completed in only 12 weeks. The bottom was protected by an anti-puncture geotextile and ballasted by cobble. The berm is covered by the geocomposite and protected by a geotextile and ballasted by soil. And the crest ballast was reinforced with the geogrid and stones. After removal of the cofferdams, the canal returned in service. Conventional methods to repair canals entail the watering of the canal, depriving people of the main source of their supply. The new frontier is to install the geomembrane underwater without emptying the canal or not even stopping or decreasing the water flow. Fiat Carpi had been the first company in the world to install geomembranes underwater in dams, where the water is not moving. So far, more than 15 underwater installations have been successfully completed. Here is a typical underwater installation. It was at Turimiquira Dam in Venezuela in 2009. The dam is 110 meters high and was affected by heavy leakages. First operation was a surface cleaning, then installation of anchoring stainless steel profiles, deploying the PVC geocomposite rolls, then anchoring the geocomposite to the profiles. For the underwater installation of geomembranes in dam, stainless steel profiles are typically used. They require extensive and expensive underwater works, but the results obtained in controlling the leakages are excellent. For installation of geomembranes in canals in flowing water, to reduce costs by avoiding underwater installation of stainless steel profiles, Carpi developed a revolutionary solution, an innovative, impermeable, heavy-duty zip. Watertight zip was especially developed by us. Its watertightness has been tested in laboratory up to 90 meters of depth, being totally impermeable. Installation of PVC geocomposite in earthen canals. Prefabricated 10-meter wide rolls of PVC geocomposite are distributed along the banks. A berm is excavated in the top part of the slope. The rolls are placed in the hydraulically driven unrolling equipment, and the geomembrane rolls are deployed underwater and automatically connected together by means of the heavy-duty zip. Then the soil is placed back again above the geomembrane to provide ballast, similar to typical canal. This very effective technology allows intensive use of local materials and contractors, simple equipment, fast operation, low cost. For waterproofing of canals, where excavation of berms is not convenient, carpenters developed the watertight mattress, the Seepage mat. Seepage mat mattresses consist of 10-meter wide panels made of two geomembranes. One upper layer exposed to water flow, and another PVC geocomposite is lower layer. The two are connected by PVC geomembrane strips as interlayer connection. The 10-meter wide panels are rolled up to make very long rolls, 10 meters wide. They are made of customized length. And they have the innovative watertight zip, adjustable flaps for easy panels connection at curves and bridges. Now we show a couple of cases where the Seepage mat has been used in canals in operation. At Ismailia Canal in Egypt, the rolls of Seepage mats have been installed over the entire cross-section. Rolls 10 meters wide are delivered to site, and a custom-made hydraulic trolley is used to deploy the rolls underwater. A second roll is connected to the first by means of the heavy-duty zip. We can see the insertion of the zip. And then the trolley takes the second roll underwater and simultaneously closes the zip. All operations are controlled by remote. The diver was just there to check, but it's not indispensable. And the second roll arrives on the opposite berm. The proper connection of the zip is checked by the diver. And a very fluid grout mix is pumped inside the mattress to provide the ballast. The grout is injected starting from the bottom and continuing on the slopes. Here the grouting operation ongoing. The installation of the mattress is completed by filling the crest anchoring trench. Thanks to the watertightness of the two membranes and of the zip, the grout is not dispersed in the water, which maintains its original quality. The installation of the mattress in flowing water was fast and efficient without interrupting the flow. The Seepage mattress is effective, durable, safe, and cost-effective. Canals is a navigational canal located in northern France. The canal is lined with concrete. The 10-meter wide rolls of Seepage mat are delivered to site. And the scope of the works here is to install the mattress only on the upper part of the slopes more affected by seepage. No berm could be excavated. So the installation was happening directly on the concrete. The rolls are mechanically anchored by divers at the boundaries, just at the perimeters. As you can see, the canal is in full operation. The zipper was closed underwater by the trolley. In this case, the rods were placed from the bottom up to the crest, while in the other project was from the crest down to the bottom. Like in Ismailia in Egypt, a very fluid grout is injected into the mattress. The injection of the grout is made only from about the water level, so there is no action going on in the water, no any risk of pollution. Yes, the mattress is in the process of being grouted. And we can see the grouting going on. Divers in the water are working on the perimeter seal, the only operation which is really done by divers. Post-construction measurement confirmed the efficiency of the solution. Conclusion: installation of PVC geomembrane system can be performed totally underwater, at any depth, at water velocity up to 1 meter per second, on the full section of the canal. No impact on canal operation. Effective long-lasting solution to stop leakage. Can be installed to repair canals and embankment dams or as an upstream plank. And it can be used in new construction of embankment dams and canals when they are built underwater. Thank you very much, and sorry for the confusion. It was pretty difficult to work together with the video going on and moving it by hand. Whatever is done.
Thank you, Alberto. It's a very impressive and innovative technology that you're presenting here. So, Adam, so the presentation will be made by Adam. He worked with Catherine on the project. So I would like to introduce both of them before Adam moves on with the presentation. So Catherine is a senior technical manager for the EMEA at Solmax, providing technical support and engineering advice to engineers, consultants, customers, testing labs, and authorities. Prior to joining Solmax, Catherine worked more than 10 years in a third-party inspection and testing laboratory for construction and geosynthetics engineering in Germany, managing testing and reports accreditation of the laboratory and site inspections. She has spent 18 years in GSE lining technology, which is now Solmax, serving for different positions and responsibilities within the company. She's an active member of DIN, CEN, ISO, DVS, ASTM, IGS, and GSI. Over the last 20 years, she has authored and presented several communications in seminars, regional and international conferences. Adam, who's going to speak immediately, he's a senior technical manager at Solmax Geosynthetics LLC. Mr. Mascal comes from the San Joaquin Valley in California. It's a very interesting feature because it's an arid area in the western US that produces 13% of US agricultural products on only 0.26% of US land. It is irrigated with runoff from the Sierra Nevada mountains by way of an extensive canal network. So it's a first-hand, it's part of the DNA of Adam, that's what I understand. Prior to his work directly in the geosynthetic industry, he worked in civil and agricultural engineering for 10 years, including a wide variety of water storage and distribution projects. He now serves as the senior advisor for a group of frontline engineers that provide geosynthetics technical support for the Americas on behalf of Solmax. So Adam, I'm going to let you start your presentation.
Right, and can you see my screen? Is my screen visible?
Yes, there is a lot of background noise.
Okay, that's my printer. Wait. Just one moment, please. There we go. I'm not sure why it decided to wake up on me for a moment there.
Okay, anyway, let's start.
Okay. Like Eric said, I'm Adam Maskell with Solmex Geosynthetics, located in the central San Joaquin Valley in California. And I'll be presenting two case histories. One is the Solano Irrigation District's Puta Canal, and another one is a more recent project in Austria. But really briefly, I'd like to just go through what I'll be talking about. I'll give a little bit of background about water in California, just for context. I think a lot of things are very similar to conditions in Egypt, which may be surprising to some, but very, very relevant. Some information about the Solano Irrigation District and the Puta South Canal, including some canal lining details and the canal today. And then another one about the more recent generation of canals. So a little bit of background information about water in California. This is taking the context of a water balance. So here's a photo of California's water demand. And the red areas are probably difficult to see, but the red areas are very high quality farmland, very rich soils, and also very near development in cities. To the south is the Los Angeles metropolitan area with 19 million people. If you were to convert to an equivalent amount of water depth demanded, it's about 2 meters per year over that metropolitan area. The San Joaquin Valley up to the north, as Eric mentioned a moment ago, it's sometimes called the food basket of the world. We get, or we need about 40 inches of irrigation demand per year to irrigate the crops there. And it's very rich farmland. And it's only about 0.25% of the U.S. area and provides almost 13% of U.S. agricultural products. So very, very rich area with quite a bit of water demand. Here's a map of California precipitation, and this is it shows the wide variety of conditions that we have in California. The Mojave Desert gets about 13 centimeters of rain per year, so very dry, arid conditions. Los Angeles area gets 25 to 40 centimeters of rain per year. The San Joaquin Valley, somewhere between 12 and 40 centimeters. And the Northern California and Northwest California and the Sierra Nevada mountains gets about 3 meters of rain per year. And what may be surprising to some, if you look at Crescent City up north and San Diego to the south, ocean temperatures off of the coast of California are surprisingly cool and bring much less moisture than one might expect. The majority of our moisture comes from Arctic storms coming from the Gulf of Alaska. But ocean temperatures are only 11 to 15 degrees C in Crescent City area, and 15 to 21 degrees C in San Diego. So surprisingly cool. California's water balance. So here's where it gets complicated. So again, back to the water supply in the Northwest and the Sierra Nevada mountains, about 3 meters per year of water surplus. San Joaquin Valley is 28 to 64 centimeters per year water deficit to make up that 2 meter demand. And Los Angeles area, again, 65 to 75 centimeters a year water deficit. And for context, over on the right, we have the major water conveyance structures in California. And just for a sense of scale, the canal network in California is about the same distance, about the same length as the distance from the south end to north end of Egypt. So the case study that I'll present is the Solano Irrigation District. It is located in the hills northeast of the San Francisco Bay Area, and it runs down into the San Joaquin Valley, and this is Putah Creek in blue, and the Putah South Canal is in green. It's about 65 kilometers long and delivers water to 3 municipal areas, and was lined in 1989 and 1993. So we have a good historical context. Design details. The canal is relatively straightforward. It's about 14 meters wide in total. The side slopes are 1.5 horizontal to 1 vertical. So steep side slopes. You can see the cross section there. From bottom to top, it's a reinforced concrete structural liner at 2 millimeter blown film textured HDPE geomembrane, and about a 5 centimeter thick fiber reinforced shotcrete, so pneumatically applied concrete protective layer. A little bit closer view of the cross section. And taking a step back here, if you look at the section A labeled, there are expansion joints, and much like we heard in one of the previous presentations, the expansion joints are a critical part of the long-term durability of the structure. Here is a detail of the expansion joint. It is about a centimeter wide and 2 centimeters deep. And the key to making the thin layer work was the blown film textured HDPE geomembrane. So a lot of these materials are relatively slick. It can make water delivery very efficient if they're used exposed, but it can offer a challenge to getting concrete to stick on slopes. So here's a photo of the installation happening in about 1993. This was the second section of the canal that was lined. And the canal today, or the expansion joint on the left, doing its job. So there was some expansion of some contraction of concrete, and that expansion joint was able to open up. And on the right is the canal itself, and you can see the relatively arid surroundings and lots of dry brush for fires, which has been interesting the last couple of years. So lessons learned on this one, on the Putah Canal. The HDPE encased in concrete, pneumatically applied concrete, has proven to be very cost effective and a long lasting canal lining system. It's in exceptional shape today. And a 5 centimeter thick fiber reinforced shotcrete, or pneumatically applied concrete, was able to be applied directly on the blown film textured HDPE geomembrane on 1.5 to 1 side slopes, and it has withstood exceptionally the exposure and canal flows. Critical to the success of the installation was the 1 by 2.5 centimeter wet formed expansion joints at about 2.5 meter spacing on a grid across the whole canal system. It contained the cracks in the shotcrete, and that allowed the shotcrete to stay adhered to the textured HDPE geomembrane below. And absolutely no dislodgement of the shotcrete layer was observed, and the canal's in exceptional condition after 28 years in service now. And on to a modern day project. This is pardon my pronunciation, but the Kraftwerk hydroelectric power canal in Austria. This was a rehabilitation of an existing concrete canal. There was very, very heavy rain during construction and installation. The liner, interestingly, the liner was not damaged even under these extreme runoff conditions. It's a 2.5 millimeter thick HDPE that incorporates a linear low density in the formulation as well, which I'll talk about in a moment. A few construction photos of this one. And so new materials, the new materials incorporate a lot of times linear low density polyethylene. It has an ability to provide extra elongation capacity to protect against punctures. So the idea being strain relief rather than strength. It proves to be very exceptionally perform exceptionally under hydrostatic conditions, especially. And the flexibility also tends to decrease wrinkle spacing and size. The other advance that's become very popular in current installations is a reflective white surface on the top side of the geomembrane. This is cast into the geomembrane. It's the same type of parent resin, but with a white pigment rather than the carbon black. This approach is proven to provide very, very effective control of temperature changes, and as a result, limits thermal expansion. This mitigates wrinkles and mitigates the risk of damage during concrete installation, and extends the working window each day for concrete installation. It's been ideal in challenging desert conditions where temperature swings can be rather dramatic, and it can be used both exposed and covered in concrete. And that is the end of it. And save questions for the end here.
So that brings to an end the presentations for today. We have several questions. So I realize it's 11 o'clock already, and that should be theoretically the end of the day. I would like to offer that we continue for another 15 minutes to go through at least the most important questions, and the one remaining that will not be addressed today could be answered in writing eventually, either directly to the people asking the question or providing a file for those interested. So I see one question here. The first one is, have they done and evaluated any major canal projects with the use of EPDM liners and the use of concrete? So maybe I will answer quickly. Yes, there are several projects done with EPDM. None was presented today. It's time limit. One very noticeable one is in Australia. It's a 150 kilometers long project. It was awarded actually by the ICID as a extraordinary and very successful project for water management of an entire scheme. Second question is, we need more information on how to select geosynthetics material for a project. What are the critical criteria for each type of geosynthetics? So I think it would take a long time to answer this question. Maybe if I can suggest that we respond to this particular question in writing, because everybody will have complementary opinions. The next one I think is going to bring more discussion. Is there a recommended speed limit for exposed geomembrane lined canals? So maybe that is something that Alberto, you can answer, you can initiate.
Sorry, I didn't understand your word. Is there
a recommended speed limit for exposed geomembrane lined canals? So you have worked on this in particular. We've seen photo with extremely high speed of water.
We have done work up to 6 meters per second. The waterhead is not an issue. We have done a project in Shaft where the waterhead is more than 500 meters. So it's just a matter of understanding the design. We are talking mainly about the products, but the real care should be devoted to the design. design is critical. Even for the selection of the geomembrane, it comes from the design. It's not that you go in a shop and you choose a membrane A, B, or C. You choose what you have to choose depending on the design done by somebody who is expert in the design.
Yeah, yesterday JP introduced the question of speed and the membrane uplift caused by the dragging forces and showed equations on how to design that. But let's say you would consider a 10 meters per second limit speed as something achievable under certain conditions?
Is achievable, but is not cost effective, because
Okay.
you have to put so many steel profiles to anchor the membrane to avoid too much deformation and bursting of the membrane and tear the membrane, that a steel lining will become more effective.
Okay.
And
Adam and
concrete
Bertrand.
can become, let's say, can be damaged more easily. So when you go, again, it goes to the design.
Understood. Bertrand and Adam, do you have anything to add on this topic? Adam?
No,
Oh,
not really. But as Alberto said, it's a question of design. It's a question of geometry of the canal also, and the weight of the membrane for us is an important fact. And as you say, 10 meters per second is quite high.
I picked this number like that. Adam, anything else you?
Yeah, I can give a very coarse rule of thumb for small installations. Typically staying below about 1.5 meters per second keeps the minor losses minor. Above that, the minor losses in a Bernoulli analysis become very significant. And so below that speed in small installations, I know that the applicability of that is fairly limited. But as a rule of thumb, if the Manning's open channel analysis it shows a flow of 1 to 1.5 meters per second, the friction and uplift tend to be fairly slight. And I think that's similar to what Alberto shared for the deployment of underwater panels that were subsequently filled. I think that's been done at about 1 meter per second, and I think that kind of corresponds with the forces being generated being relatively minor. And Alberto can correct me if I've misunderstood that, but anyway, that's what we've seen in small canal installations.
We are talking also about hydraulic tunnel. We are talking about we are talking about a hydroelectric project. Is always a canal. Just the water speed is high.
Understood. Okay, so next question: is canal lining so advanced in Egypt that every speaker has cases from this country?
Sorry?
Is canal lining so advanced in Egypt that every speaker has cases from this country? So we heard cases from Alberto, from polyethylene, from others. Bertrand, do you have case histories in Egypt as well?
No, I think the question is going to Chris and Hervé, because they gave a lot of examples of canals in Egypt.
Hervé, Chris? We don't hear you, Hervé. You're muted. We don't hear you.
I think maybe if I speak first, the canal that I was looking at, the works are relatively small, where they're trying to put in the marrows, which actually are plastic pipes rather than get going for lining canals, open canals. So that was done under the FIMP project, and that was very, very successful, because not only did it was extremely successful in saving water. If you look at the whole concept, because the irrigation department looks after the canals up to the the distribution canals. There, the farmers were prepared to pay for the installation of a pump station, so a single pump station instead of having multiple pumps, and then to have a water use organization which operated the pump station to deliver water through these buried pipelines to individual farmers. And I had one farmer say to me that he's now become a gentleman farmer because all he needed to do was to pick up his phone, and he phoned the pump operator and find out when his pump was going to be operating, and then he would walk down to his farm edge and turn a tap and his field was irrigated. So the amazing thing there was that the farmers were prepared to pay for that, so that once the installation was done, the costs were calculated, and then the farmers paid an additional tax for that installation that had been installed. So that was, as I said, about 100,000 hectares has been completed in that way. And I think that's a tremendous advance if you look at the start from at the distribution, where you have multiple pumps, to having a single pump station with a farmer operating a single outlet for his field. That is the saving of, something like 60% of the water losses at that stage.
So the situation is,
if Egypt is looking to save water, it's amazing how much water they can save where the farmers are prepared to pay for that installation. And that, I think, is something which they need to pursue.
so that supports the concept that in Egypt they have such a critical problem and they are very advanced in this.
They were, but this was an experiment. In fact, FIMP was done as partly experimental, but they need to make a decision whether to extend that to elsewhere, and that I think is where they're at.
I think Chris has focused essentially on saving water in the minor and small canal near the farm, with all the problems, social problems. But the example of the Toshka Canal, which was built 15 years ago, about completed, it shows an example of excellent application of technology and selection of geomembrane. Now, Egypt is embarking in this canal rehabilitation project involving thousands of kilometers of canals, using essentially rock masonry protected with a relatively thin concrete layer. So maybe tomorrow we'll have more discussion about these mega projects.
Yeah, I think we're both quite concerned because they, as you say, coming from Egypt, that's the design which they've got for these new works. I think they're rushing into them and not necessarily putting in any geomembrane. So my concern is I've heard from one project that they were talking about maybe putting in a thin membrane, but I think the works which the minister showed was the lining works being done without any geomembrane. But as I said,
well, it's a partly in some they put some geomembrane. They are concerned about seepage control. In other cases, they are essentially concerned about erosion control of the canals. So there are two different objectives. Maybe Eric, if you since I have the floor, I can just try to answer very quickly. One question was raised yesterday about the cost of using geomembrane, but it's just in one word. If you use exposed geomembrane, and there are some examples, the solution is cheaper than using concrete lining. I'm not talking about extremely sophisticated case underwater. I'm just talking about under dry conditions. Now, if the geomembrane is protected with concrete, probably it's a little bit cheaper than, more expensive than only concrete, but not much, because you can, the concrete in this case is not a structural, it's just to protect the geomembrane, and instead of 10, 12 centimeters, you can reduce the thickness of the concrete to 6 centimeters, maybe, or 5, 6. So you make some saving on the concrete itself, on the protection. So in that case, it may be a little bit more expensive, but not much.
And using creative options for the veneer on top of the geomembrane may also reduce the cost the cost of the veneer.
Yeah.
So maybe we have many other questions. So if you're okay, we can continue with the others. Actually, the next one is in line with the discussion. Can geomembrane be placed on top? The geomembrane placed at the top of supporting materials can be placed on top of the supporting material. So is it right also to use concrete as a supporting material? I think this has been answered already. Yes, the geomembrane can be placed over concrete. There are experiments with bituminous, with every material. So the next question is for Mr. Brull. Bertrand, what are the environmental and human health impacts of the heated bitumen? So
the binder used to manufacture BGM is made with a very high quality bitumen, and it's a very stable type of bitumen. So therefore, it's not harmful for people and the environment, and also the heating time of bitumen is only when you weld two panels together, and so it's very limited, and most of the time it's outside. So it's been liquid or vapor for less than 10 seconds.
I think the underlying question was, is it necessary to wear personal protection equipment to do the welding or not?
Against heat, yes, but that's it.
No, not the fumes?
No.
Okay. So the next question is more commercial, and I prefer to leave it aside. It's about comparing materials, one of them not being presented yet. So next one is for Bertrand again. You mentioned the bituminous geomembrane was mechanically fastened on top of slopes in the French reference. How was it anchored in the rest of references with earth substrates? Only trenches on the crest of slope? Any transversal anchoring?
So it's, yeah, for most of the example, the other example, it's an anchor trench on the crest of the slope. So along the canal, you can do horizontal anchorage, so weight on top of the liner with an additional staples all along the canal. And you can also do transversal anchoring if you need it. So the fact is that when you reline a canal, at some point you need transversal anchoring at the end and at the beginning of the project, because for the example of the canal in India, it's more than 100 kilometers of canal to reline, and they did just a section of one kilometer. So there is a transversal anchorage at the beginning, so upstream and downstream. So this is a possibility too.
Okay, there are some questions which there is one question which is specific to design loads. Maybe that's something that can be answered in writing as well in the future. So another one about the speed for wind uplift. For Bertrand, you said about the resistance of the bituminous geomembrane against wind. What is the maximum wind speed that the geomembrane can withstand without additional anchorage? So the maximum wind without specific anchors.
So it's for sure it depends on the weight, thickness of the BGM you're choosing. But in general, we say it's 35 kilometers per hour.
Thank you. So question for Mr. Squero. How did they attach the steel beam on the canal? Before the PVC or after installation of the PVC?
Usually the system is with pretensioning a couple of profiles which allow tensioning of the membrane. So there is one profile which is anchored to the concrete, then the geomembrane is placed over, and there is a second profile which clamps the membrane against the inner profile. So we have one steel profile below and one steel profile above, which usually is covered by a PVC strip.
Okay. Next question would be for Hervé and Chris. Is fire performance an important parameter in the selection of geomembranes in canals? In some areas, the bushes at the side of the canals are removed with fires. Could a flammable liner spread the fire?
I think that the short answer to that is that the geomembrane is generally covered with concrete, so it's unlikely that any fire is going to come to within a distance which is going to affect the lining. I don't know whether Hervé would like to add that. I don't know, in Tosca, where it's a much bigger canal, there may be a problem.
I think that questions should be more to Adam or Bertrand.
I can speak to that.
The geomembrane can resist the temperature of the fire.
I can speak to that. I've seen the results of fires with polyethylene geomembranes, and the material can be burned, but as soon as the source of heat's removed, it tends to extinguish itself. So we've seen fires with fuel spilled on surfaces of ponds and things like that. So again, the membrane will be damaged if it's exposed to significant fire, but it can typically be repaired. The material extinguishes and a patch can be installed if it comes to that.
I've never heard of any example like this.
Okay. I'm going to handpick a few additional questions because it's already 11:20. What is the typical design life of bituminous geomembrane, and what are the factors considered to determine this?
Main factor is if the liner is exposed to UV or if it's buried or covered by any type of material. So that's the main question. So when it's exposed, the design life is smaller than when buried, and we can say we have experiences until 40 years old geomembrane, and we expect a design life of 50 years, whereas when it's buried, some studies made by a French body, government body, because BGM has been used to cover medium and low radioactive waste, and it determined that after 300 years, the liner will lose 3 millimeters of thickness, and 3 millimeters of thickness is less than the thickest product they use on site.
Okay. I have another question which I think is interesting to address. Does using the textured geomembrane has any advantage versus smooth geomembranes in canal lining? So I think Bertrand has a strong opinion on this. You showed the dogs walking on the surface and so on, but maybe Adam and Alberto, you can contribute to the discussion on the surface texture.
I can speak some to that. The surface texture has proven to be very effective in placing concrete on slopes on top of the membrane. It does provide some anchoring that is very, very helpful during construction. Hypothetically, it could be used to retard the flow rates if more time of concentration is needed, but anchoring would need to be really carefully considered. Typically speaking, if we're talking about safety, typically speaking, it's better to install ladders, as even textured membranes when wet are very, very difficult to climb.
in Australia during the last 15, 20 years, they're using exposed geomembrane. Initially, they used HDPE, which was very slippery. So a number of kangaroo fell into their canal, and I think there were 1 or 2 casualties also. So they have, after some experience like this, they have a shift to using EPDM, which is more easy, which is less slippery than HDPE.
Alberto?
Well, let's say to have a low friction losses, you have to have a smooth membrane. If you have a smooth membrane, it's more difficult to climb out. So you have to decide what is your goal. You cannot have both. And usually they in a project we installed a gabion without stones to allow to create the friction for animals to get out. So we have the smooth membrane below, but we have the mesh on the steel mesh on top.
All along, or just at some place?
This was just in the fluctuation zone, 1 meter below the fluctuation level, so yeah, people can put the foot and they can grab the mesh in any place. But again, this is a design and a financial choice. It's not really technical.
So there is no universal answer. Maybe a last question, which I hope it's not, the answer is going to be not going to be too long. I would like to have your comments on how the geomembranes are to be treated after service life in terms of recycling, environmental impact, especially those ballasted with concrete or those being grouted.
I can start. I can say that PVC can be recycled, and PVC is not sticking to the concrete. The concrete is independent between the two geomembranes. So concrete will be recycled as usual, and the PVC will be taken to some plants where they do recycling of PVC. So nothing difficult, nothing special.
The same goes for polyethylene as well.
Bertrand?
I think I didn't follow the
it was about post-service life of geomembrane. What are the plans and options, possibility for treatment of the material, so recycling or whatever, landfilling? What are there any solutions available for bituminous geomembranes?
Bituminous geomembrane can be reused, let's say shredded, and then reused to in asphalt concrete for road construction.
Okay, so
in general, if the liner is covered with concrete, with BGM, you don't need any geotextile in between, so there is quite a good adhesion between the geomembrane and the concrete. So it's quite difficult to manage them.
Okay. So we are already half an hour behind 11 o'clock or 6:30 in Egypt, 5:30 in continental Europe. So I think we need to bring an end to the workshop for today. So we will we will do our best to make available the presentation, if possible, if authorized by the speakers, and the videos online. The question and answer, we're going to prepare a file and distribute the answers to the questions that were not answered live. And we hope to have everybody present today, tomorrow, when we reconvene for the third day of this series of 3 workshops focusing on canals. So thank you for all the authors, Hervé, Chris, Alberto, Adam, Bertrand. Very instructive presentations, and have a good rest of the day.
Thank you very much.
Thank you.
Have a good day.
Thank you.
Bye-bye.